Welcome to BKW Physics. I'm Mr. McConley. Today's topic we're going to talk about is momentum and impulse. And I want to start with an example. When you are standing near the edge of a road, for example, and you go to cross the road, and there's some vehicles coming down the road, if you see a huge dump truck that's loaded, and it's coming down the road, you're like, oh, you have some, like something inside of you has some respect for the size of that thing, and you have a little bit of fear. Now, if you see a motorcycle coming at the same speed, you know that if you were to walk in front of a motorcycle, it would still be really bad for you, but you don't have that same sense of like, ooh, that's really scary. It's a motorcycle, it's kind of small, and you're just not that scared of it. And this idea here is because you have this internal understanding of what momentum is. So, before I really get into that though, back up. We did inertia earlier this year. And by all simple definitions, how do you define inertia? What was it? Volunteers, please.
Non-driven motion, which is the same motion.
Yes, that was Newton's first law. So an object in motion wants to stay in motion, an object at rest wants to stay at rest, and the idea of inertia is all based on one thing. What's the one thing it's based on?
Mass.
It's all based on mass. So it's the first law,
Good job, Sir Roger.
and it's all based on mass. So good job, guys, both of you. So that's inertia. And to a certain degree, my example I gave a minute ago with the dump truck and the motorcycle is an inertia thing, because you know that dump truck has a lot of inertia. But there's more to it, because there's another factor involved here, which can make it so that momentum is equal even if the mass of two things are not equal. Let me explain. So if that dump truck's creeping along, just going slow through a school zone at 20 miles an hour, it's going real slow, it's got a certain amount of this stuff called momentum. And if in that same school zone there's some illegal person performing an illegal act on a motorcycle, they're going wow right through the school zone at 80 miles an hour, it is possible that the momentum of each of those, the motorcycle going really fast and the dump truck going really slow, could actually equal one another. They could have the same momentum or have the ability to do the same damage. But that's because when you switch to momentum, here's where the new stuff begins. Momentum is based on two things. It's based on mass, just like inertia was, but it's also based on velocity. So when you combine mass and velocity, you get an idea of momentum. The equation is really simple in physics. This rho means momentum, and it's equal to mv, which is the way you'll find it in your reference table as v. So momentum is mass times velocity. And velocity is in meters per second, and mass is in kilograms, so kilogram meter per second is momentum. So now you can kind of see back to my example. If the motorcycle has a very small mass, but it has a very high rate of speed or velocity, then that actually can end up equaling out something that has a very large mass, but a very low velocity. When you multiply them together, you can end up getting the same number for the two examples. And the Regents, just so you're aware, it's always trying to confuse you on these two. And I noticed on the June 2003 was a really confusing question about this, but there's been others since then. But basically, they will try to confuse you into mixing these two ideas. Inertia is just based on mass, momentum is based on mass and velocity. You gotta keep that straight. So, real quick as an example, if my mass is 95 kilograms, and I am moving at a velocity of 10 meters per second, what is my momentum in that specific instance?
950.
You just times them together. You just do 95 kilograms times 10 meters per second, and it's basically adding a zero. It's 950, just like a lot of you instantly said when you saw this, kilogram meters per second. Fine. But then we move into something a little bit different. It's just an extension of this momentum idea, and it's called impulse. So the way I'll explain it to you is this way. You're all familiar with F equals ma, which is Newton's which law?
Third.
Just only a second.
That too.
Third, good guess, huh? Third is the equal and opposite forces, but the second is if there's a force, it causes an acceleration, F equals ma. That's the second one, which is not written exactly like that in the reference table. It's A is F net over m. This is the reference table way of writing it, but same equation, just rearranged. So if I start with F equals ma, though, because I like it being in that form, and then instead of the A, I do change in velocity over time, because remember, acceleration is a change in velocity over time. Okay. So I substituted that in here. What you'll see appearing is the fact that there's an m and a v here, like momentum. So I'm going to multiply the t to the other side, so it's f times t, as you multiply that to the other side, is m times the change in v. So what I'm getting at here is on the right-hand side, m times v is equal to our new concept called momentum, right? So this is like our new concept right here. Well, f times t is an equivalent statement, but it's not called momentum. This equivalent statement on this side is given the capital letter J. And the capital letter J is impulse. I don't know why they used a J, except that I is probably already used for other things at that point, and so they went with the J. So what impulse is if you're a boxer, Rocky Balboa boxer, okay, and you hit the other person that you're boxing against, you are going to supply a force for a certain amount of time that your hand is in contact with the person, so it's a force times the time, and that is called an impulse. But when you do that, it will be exactly equal to the momentum that you imparted. The word is imparted. You impart momentum to the other person. So you take your force and your time and you hit something else and it imparts momentum to the other object. It's like in a car crash. One car is going along and it has momentum. And when it hits the other car, it gives the other car an impulse because it hits a force times the time, which gives that momentum or trades that momentum to the other vehicle, and that car jumps forward when you run into it. Or you can think of it like you're playing pool. And you hit the ball, and the one ball hits the other ball. You are trading impulse momentum between the two billiard balls. Does it make sense how that works? So this can be used in a whole variety of ways, but as one example, back to what I started with. I'm going 10 meters per second. My mass is 95. What if I run into somebody by accident as I'm walking down the hall, and because of the collision, I slow down to a velocity, let's just lose one, to a velocity of 9 meters per second. So I'm going 10, I weigh 95, or I have a mass of 95, I bump into somebody, it slows me down to 9 meters per second. I'm in contact with the person for 7/10 of a second, so I'm in contact for 7/10 of a second. How much force did I apply to that person? I'm trying to give you a little bit of a, an example that could be a realistic example. So, what do I do? I'm looking at this here. What are all the things I have? Well, I'm looking for force. I got time, mass, velocity. Okay, so I'm going to set these two things equal to each other. F times t equals m times the change in v. I'm looking for force, so I'm going to divide the t over to the other side, because we like to rearrange first in this class. The mass is 95 kilograms. My change in velocity, how much did I change my velocity between before and after?
1 meter per second.
Yeah, 1 meter per second. And my time that I was in contact for is 7/10 of a second. So our handy student Jolene is going to punch this up for us and get a number on what we have for the force. And by the way, what will be the units for force? Forces are always in
Newtons.
Newtons. So we're going to be in Newtons right here. What do we got?
Negative 135.
I don't think it's a negative.
Yeah.
Just 95 divided by 0.7. Hit that up again. I'll do a double check here in the front row.
135.7. Are you still there?
Yeah, that sounds right. 135.7,
Yeah.
so I'll make it 136 newtons. So you're going to hit that person with 136 apples worth of force. Okay? Because remember, Newton's, like, we think of it like an apple. Okay? So for today, that is the concept, or the connection between impulse momentum and inertia physics.